Hello, everyone. First, I would like to thank you, all the organizers of this conference, for inviting me. So, my talk is about to study the variability of quasars as a function of rest frame wavelength from the Zwicky transient facility. So, this is the outline of my presentation. First, I will briefly mention about the motivation behind this project. Then I will tell about I will tell briefly about the active galactic nuclei. Later, I will move to the data analysis part of this project. Here on the right, you can see the optical light curve of the Seyfert 1 NGC 5548 galaxy. This is one example of the varying light curve of the active galactic nuclei. So in order to understand the reason behind this variability, we want to understand what is the relation between the variability of the active galactic nuclei and the rest frame wavelength on long and short-term time scale. And when we obtain this correlation, we can also find the AGN physical characteristics, and it will be helpful to constrain the accretion disk model. So here in the bottom, this is the cartoon for the Keplerian accretion disk. So in the center, this is the black hole, and then around that, this is the different annuli which represent the accretion disk. So the assumption is that this accretion disk emits the black body radiation. So we expect that there should be a higher temperature near to the center, and then the temperature decreases as we move outward to the accretion disk. So if we plot the power spectral density for two different wavelengths that is shown in the top, so we expect that there should be a higher amount of normalization for the G band as compared to the R band. So there are some models that describe the AGN variability, and here I will be explaining about the two models. The first one is the reprocessing model on the left. So in the center, there is a black hole, and on the above, the corona is shown by the orange, and the accretion disk is shown by the blue part. So the corona emits the X-ray, and this X-ray gets absorbed by the accretion disk, and which reprocess this X-ray from UV to the infrared. So this reprocessing model is able to explain many observational facts and also the temperature profile of the accretion disk. But there are some limitations of this model. For example, is that this model expects that there should be a tight correlation among the variability of different wavelengths. But in the observed data, in many AGNs, we do not find this tight correlation. So in the right, there is another model that is called CHAR model, Corona-heated Accretion-disk reprocessing model. And this model is able to overcome this limitation. So in the right, the black hole is shown in the center, and then the accretion disk is shown in the gray, and the corona is in the light blue. So according to this model, the accretion disk and the corona are tightly coupled, and the magnetic turbulence in the corona causes the X-ray radiation, and this turbulence gets propagated to the accretion disk, and this causes the heating effect in the accretion disk, which then induces the change in the temperature fluctuations. So there have been previous studies they have reported the anti-correlation between amplitude of variability and rest frame wavelength. So in the right, this is the plot of the structure function versus the rest frame wavelength, and these different contours represent the different filters, and the red line represents the median power law. So we wanted to confirm this study because the amplitude of variability also depends on the black hole mass and the Eddington ratio. So it makes it challenging to understand the relation between the amplitude of variability and the rest frame wavelength. And for this project, we are using the ZDF data release light curves, which has cadence of 3 9, and also the baseline is of 3 years in length. So on the top right, this is the G band light curve, and then in the bottom, this is the R band light curve. And we need the good sample to do this project, and for this we took the sample from the SDSS data release 14 quasars, where they have reported the black hole mass, Eddington ratio, and redshift. And the sample covers the redshift range from 0.1 to 0.8. And in this sample, the black hole mass is estimated by the H beta line, which is the best mass estimator. Also, the final sample contains the 3000 G band light curves and around 3400 R band light curves. So after extracting the light curves for this sample, we obtain the variance, and this variance can be described as the measure of the variability amplitude. And to understand this, on the left, this is the power spectrum density of AGN, which is described by the broken power law. So in the region 3 and in the region 2, the AGN follows the red noise, which can be expressed as directly proportional to 1 by alpha, where F is the frequency and alpha is the spectral index. So when we plot the variance values as a function of the time scale, we obtain the power spectrum. And in this project, we are using the Mexican head filter to obtain the variance, which deals with the uneven sampling of the light curves, because the ZTF light curves has yearly gaps. Also, later, after finding the variance for these light curves, we wanted to make the sample homogeneous because the variance depends on the black hole mass and Eddington ratio. So on the top right, this is the histogram of the black hole mass, and on the bottom, this is the histogram of Eddington ratio. So here we can see that there are certain range in the black hole mass and Eddington ratio in this sample. So in order to make the sample homogeneous, we scale the variance with the black hole mass of 10 to the power 8 solar mass and Eddington ratio of 10 to the power minus 1 from using the table from the Arévalo et al. 2022. And since we obtained the variance for 2 time scales, so we did this scaling for both time scales. And after making the sample homogeneous, we study the variance as a function of rest frame wavelength. And for this, we use the Redshift as the tool to study the different rest frame wavelengths, because the sample covers the redshift from 0.1 to 0.8. So we obtain the rest frame wavelength by dividing the bandpass filter to 1 plus redshift.
Please note you have 5 minutes left.
Yeah, thanks. Here, this is the plot of the variability versus the rest frame wavelength. So on the left, this is the plot for time scale of 150 days. And on the right, this is the time scale of 75 days. So to find the relation, we group the variance into the 17 beams of rest frame wavelength, and each value in the rest frame wavelength represent the median value. And we also perform the linear regression for both time scale data. So here we find that the variance is anti-correlated with the rest frame wavelength for both time scale. Also, we find one interesting result that the slope is steeper for the short time scale. But in this plot, if you see in the x-axis between 3.50 to 3.55 and 3.65 to 3.68, there are some wiggles. So we wanted to understand that what is the reason behind these wiggles. So for this, we overplot the template of the spectra on the top of this plot. And if you see around 2,800 and 4,800, there are suppression in the variance because of the broad lines. So that's why we wanted to recover this variance, and we obtain the new variance that can be obtained by using this formula: log of new variance equal to log of variance plus 2 into log 1 plus f, where f is the ratio between the flux of the emission line and flux of the quasar continuum. So
3
this
minutes
is
left.
the new variance. We did this correction for both time scale, and the orange points represent the corrected variance. So here we can see that the new variance is a little bit higher than the variance obtained before. So after this correction, we also find the variance ratio, and this variance ratio is the variance at the 150 days time scale to the variance at 75 days time scale. So now we will term it as the observed variance and observed variance ratio, the new variability features. So in this case, you can see that we found a positive correlation between the variance ratio and the rest frame wavelength. So later we also compare our result with the CHAR model, and in the both time scale, when the CHAR model variance is represented by the blue and the observed variability is represented in the orange, and we find that the CHAR model agrees with the slope of the plot of variance versus rest frame wavelength, but the y-intercept are significantly different. And we also compare the CHAR model variance ratio to the observed variance ratio, and in this case also the slope agrees. However, there is a difference in the intercept. And to understand this correlation, we plotted the power spectrum for two different wavelengths. Shorter wavelength has like a higher amount of normalization than the longer wavelength, and we also expect that there is a relation between the slope and the rest frame wavelength, if we will assume that the slope is related to the variance ratio. So we expect that there should be a steeper slope for the longer wavelength, so which is shown in the bottom right. So here, this is the summary of my presentation. Thank you.